Problem number 18. A small chunk of ice falls from rest down a frictionless parabolic ice sheet, like here on the figure. At the point A in the diagram, the ice sheet becomes a steady rough incline of angle 30 degrees with respect to the horizontal and the friction coefficient mu, unknown coefficient. This incline is of length 3/2h. h is initial height. The chunk of ice comes to rest precisely at the end of this incline. So what is the coefficient of friction, mu? So in this problem, the best way to do is to use work energy theorem. So it means that our potential energy initially go into kinetic energy for this chunk, but because it's come to rest in the end, it means that all this energy will spend for friction, for work of force of friction. So we need to just to write this equation. Potential energy, which is mgh, that's equal force of friction multiplied by length, which is 3/2h. So force of friction equal, we know it's a coefficient of friction multiplied by normal force, and normal force equal mg multiplied by cosine 30 degrees. So when we put all these meanings here, we can get final equation mgh equal mu mg cosine 30 degrees by 3/2h. So we have mgh cancelled, and finally we have mu equal 2/3, 1 cosine 30 degrees. Cosine 30 degrees is √3/2. So we have finally 4/3√3. So we can use calculator, and the answer is B, 0.77. This is the correct answer. Problem number 19. A non-Hawkian spring has force like this. So we see it's not proportional to a displacement, it's proportional to quadratic to displacement, where k is the spring constant and x is the displacement from its unstretched position. For the system shown of mass m connected to an unstretched spring initially at rest, how far does the spring extend before the system momentarily comes to rest? Assume that all surfaces are frictionless and that the pulley is frictionless as well. So angle is 30 degrees, and to solve this problem we need to use energy work theorem. It means that whole potential energy for this mass during after its stop, it will go to potential energy of this spring. So potential energy, if we have total displacement is x, so total potential energy will be mgx multiplied by sine 30 degrees. And that's equal to potential energy of the spring. We know that for a regular Hookean spring we have potential energy equal 1/2 kx square, but in our case we need to do integration, because if we have graph force as a function of displacement, in our case it's parabola. So to find what is total energy, we need to count what is the area under this curve, which is integral. And I can remind you what is the integral from polynomial. If we have polynomial function like x power n dx, integral will be 1/n plus 1 x power n plus 1. In our case n equals 3, so we can say that integral from kx square from 0 to x dx, that's equal 1/3 kx cube. And this expression we can put here, 1/3 kx cube. So we see that sine 30 degrees is 1/2. 1 time x is cancelled. We have here x square, and after simple calculation we can find that x equal this expression a. So this is solution. Problem number 20. A point like mass moves horizontally between two walls on a frictionless surface with the initial kinetic energy E. With every collision with the walls, the mass loses 1/2 of its energy to thermal energy. How many collisions with the walls are necessary before the speed of the mass is reduced by factor 8? So V is reducing to 1/8. To solve this problem we need to write expression for kinetic energy. That's 1/2 mv square. So we see that if speed reduces 8 times, it means that kinetic energy reduces 64 times. So we have kinetic energy going to factor 1/64. But we know that after each collision we're losing 1/2 energy. So we just need to equalize this 1/64 to 1/2 power n, number of collisions. So it means that we have 2 power n equal 64 and n equals 6. So this is correct answer, C. Problem number 21. If the rotational inertia of a sphere about an axis through the center of the sphere is I, what is the rotational inertia of another sphere that is the same density but has twice the radius? So we just increase radius twice. We know that for solid sphere we have rotational inertia, it's 2/5 mr square. But suppose we forgot this coefficient in this problem, we don't need this. So it's like beta mr square. So to solve this problem we need to count what is the new mass and put this new radius. If we increase radius twice with the same density, we increase volume 8 times, it means that mass will increase in 8 times. So we have I prime equal beta by 8 mass and the 2 radius square, so which is 32 times beta m r square, which is 32I. So that's our correct answer.